Thanks very much, Shiri, for presenting and for giving me the opportunity to present my work within the framework of this virtual seminar series. Good evening for those sitting in Australia. Good morning for those sitting in Europe. Apologize for people sitting in America. So I guess the talk will be recorded. Can you confirm, Shiri, that it will be recorded and available on the website?
Yes, that's right. We're recording this and it'll be on the website.
Oh, thank you so much. So I gave kind of a short title, which is Formation and Preservation of High Temperature, Ultra High Temperature Terranes. Those who know me and have read some papers, I'm a hard rock geologist, but what I will present today, I will focus on the interplay between the partial melting, which has weakening consequences on rocks from the crust, and granulite formation, which is rather strengthening rocks from the crust, and the control of this interplay on orogenic processes, and this from a thermomechanical modeling point of view. I've been here in Sydney for the past 18 months working with Patrice Ray, and I'm very thankful for the European Union funding my H2020 individual fellowship to learn complementary skills. So to start with, I will take 10 to 15 minutes, a little bit of a detour before really digging into and giving you some insight about the formation and preservation of high temperature, ultra high temperature terranes. We'll take a detour and with an example that we've recently published in Geology a few months ago of how we use the thermomechanical models and the basic principles and phase changes that need to be implemented to answer and work towards answering this question. In this slide, can you see my mouse moving?
Yeah, I can see that.
We'll take a 10 minutes detour. An observation from looking at crustal thickness that has been recorded in stable continents is this diagram from the USGS. USGS. On x-axis is the crustal thickness and y-axis number of observation. We basically teach first-year students that the average crustal thickness is 40 kilometers plus or minus 1 kilometer. But looking into details, there is quite a large variability, with some places where the crust can be quite thin, down to 30 kilometers, and some places it can be quite much thicker, like 60 kilometers. And how come we can preserve this crustal thickness heterogeneities in stable continents? Looking at some examples, the top diagram figure on this slide is a cross-section in the Canadian Shield along the Torngat Orogen. So this is a cross-section, the x-axis is the distance, this is 400 kilometers, the y-axis is the depth down to 50 kilometers. First of all, in this cross-section derived from seismic studies, we noticed that the crust can be on the left-hand side, the west part of the cross-section, around 35 kilometers thick, whereas we can have this crustal root in the middle of the cross-section down to 50 kilometers in depth. And seismic velocities increase in these crustal roots, indicating that the material may be of a different nature. At a different scale, the figure below is a map of Australia, a MOHO depth map of Australia with the color code. The lighter the brown indicates crustal thickness about 30 kilometers, and those dark brown pods indicate crustal thickness up to 65 kilometers in the Northern Territories and in the Mount Isa area. So at continent scale as well, there are some crustal roots and crustal thickness heterogeneities preserved even far away from active tectonic regions. How come? Can we find an explanation for that? The numerical modeling approach we are using in this entire set of experiments is under role 2, which is a fully coupled thermomechanical modeling tool. We can give models in 2D and 3D. I will work on in 2D for the sake of this presentation. And you can have more information under underworldthecode.org, and this is an open source community code developed in Australia. Let's now have a look at the starting conditions we have chosen for our experiments in order to understand how we can form and preserve crystal thickness heterogeneities. This is a model box of the initial conditions for our model. This is a box. In x-axis is the size of the box, which is like 360 kilometers. In y-axis, this is the depth down to 100 kilometers. So we start with a thick crust here in orange and brown. This is a 60 kilometers, 70 kilometers thick crust. They can be associated to our orogenic plateau, a thick orogenic plateau like we can have in Tibet, and related collapse. So in our experiments, we stretch gently at different, we test different velocities, one a little bit faster, the other a little bit slower, and we just stretch the crust and let it return to a roughly normal thickness of 40 kilometers. And what is interesting and what is quite novel in this series of experiments we have performed is that we are implementing first order metamorphic phase transition. We consider that this orange color, brownish orange color, is the continental crust that can be stable in amphibolite facies condition. On the bottom right of this diagram is a metamorphic facies diagram that we can find in every textbook for metamorphic petrology. We consider this brownish domain amphibolite facies condition stable for 500 to 700 degrees C below 12 kilobars. And we consider as well the formation of granulite, which is this high temperature field on the bottom right of this metamorphic facies diagram, which is stable above 800 degrees. So we have implemented in our model, we allow the crust to experience a prograde metamorphic reactions from amphibolite facies condition to granulite facies conditions. And we chose to set this temperature boundary at 1050 K, which is a little bit above 800 degrees. But what's interesting as well is that we know, all metamorphic petrologists in the attendance know that a retrograde reaction, rocks do not recalibrate at every step of their history. And this is what is usually implied in a lot of numerical models who take into account metamorphic phase transition. But every field geologists know that thermodynamics is, thermodynamics rarely occur, metastability is the rule. So in order to take into account of this phenomena as well, that the retrograde transition of the rocks from granulite facies condition down to amphibolite facies condition is of course dependent of temperature. So we set this temperature boundary at 1050 Kelvin. But in nature, what triggers a retrogression? Either it is fluid flow, which is quite different to implement in this kind of numerical models, and it is deformation. From the field, we know that in shear zones, rocks are most likely to recalibrate into the new pressure temperature condition than in Budas. So we've associated to the retrograde reaction from granulite to amphibolite a strain rate condition. So when the rock reaches a certain temperature and a certain strain rate, which is like 10 to the minus 14 in this experiment, they will be transformed in retrograde crust. And the last parameter we play with is the solidus and liquidus temperature for the continental crust, and so which is supposed amphibolytic or considered amphibolytic, and the granulates as well. So as a consequence, the starting conditions are a 60-kilometer crust in orange considered amphibolytic, and at the bottom of the crust is granulitic or garnet pyroxene crust, which I shorten as granulite. Some petrologists in the room may start to shout, but let's make it simple. I've learned that with models, we need to really work at first order, and we cannot take into account chemistry and all these kind of heterogeneities that we can have in real life. So let's have a look at how these models work at first order. I can't resist showing you a beautiful picture of a migmatite, which is a partially molten rock from the southern granulite terrain where I did my PhD 20 years ago. On the top part of this photo, there's a slightly foliated gneissic domain with biotite and quartz feldspar layers, and the bottom part of this picture is a leucosome, a leucocratic domain, mainly composed of quartz and feldspar and tiny euhedral incongruent garnets. And this leucocratic domain or leucosome is interpreted as crystallized melt. This is how a migmatite and a partially molten rock looks in real life. It's quite heterogeneous. On the other hand, how can a granulite look like? This is one which I've sampled in the Antana River block in Madagascar. This is a coarse grain rock with those euhedral garnets, and into dark moss. This is mostly orthopyroxene and biotite. So both rocks look quite different. So let's first look at one of the movies or one of the experiments we've performed when we start with this thick crust, like 70 kilometers thick crust, and we start stretching it. So what happens? So the crust starts to thin, but during this thinning process, so part of the granulite are being retrogressed in high strain zones. The crust thins heterogeneously, and when it returns to roughly 40 kilometers, it does preserve crustal thickness heterogeneities with some thicker crusts with boudins dominated by granulite and some necks which are retrogressed here in light blue. And overall, even though we have let the experiment relax 200 million years, we've only stretched for 10 million years, and then we stopped the kinematic, we set the kinematic condition to 0 and let the crust relax. And even after 200 million years of relaxation, we do preserve crustal thickness heterogeneities with boudins, thick crust dominated by granulite, and some retrogressed domains as well. So let's now have a few screenshots of some N-numbers models and go back to the models we've seen in the movie at the next slide. So in this set of experiments, the top picture over here is a screenshot when the crust has roughly returned to 40 kilometers. So we've stretched the plateau up to until the crust has returned to roughly 40 kilometers. And this first experiment on the top, we have only allowed the crust to melt. We didn't allow in our experiment to form granulite. In that case, we have a thick layer of partially molten crust here in purple. In the middle of the experiments, we have a beautiful gneiss dome, migmatite gneiss dome, that is being exhumed in the middle of the model. And this confirms the results that have been shown by Patrice Ray and different co-authors on the exhumation of the weak crust and formation of megmatitic dome. The bottom experiment, the bottom screenshot here, is taken at the same, after the same time of stretching. But in this experiment, we've allowed the crust to be transformed into granulite. We've allowed the granulite to be retrogressed into the crust as well, retrogressed crust here in pale blue. But we've kind of played a little bit with the solidus of the crust and put it at an average temperature at around 720 degrees, which is roughly, can be the solidus of unfertile metasediments. In that case, we do preserve crustal thickness heterogeneities as well, with boudins located basically with the granulites located in the core of the boudins and the neck are retrogressed. What is quite interesting as well is that in the upper crust, deformation is quite strongly partitioned here in those shear zones. So these are kind of two end members models with allowing a lot of melt and allowing less melt with less fertile rocks and more granulitization. Let's now have a look at an intermediate model in which the formation of granulite is allowed, occurring here in dark brown in pods at the bottom part of the crust. And we allow as well the crust, the orange crust here, to melt at quite a fertile solidus, like fertile metapelite, around 650 degrees. In that case, the crust and the retrogressed crust in pale blue does melt, which makes these purplish pods in the neck of the boudins. If we zoom in the right part of this diagram and look at the velocity vectors, even after extension is ceased, we notice that we have kind of a bimodal mixed behavior of the crust. In the thick part of the crust, the granulite pods and boudins are immobile. Whereas within the neck of the boudins, the partially molten crust really would like to move upwards and is quite mobile, weak and mobile. So this is quite an interesting phenomenon. We do not really have a flow of the lower crust totally partially molten, but we still have some cores which are immobile, implying that we can have kind of a mixed behavior of these orogenic domains. And of course, crystal thickness heterogeneity is preserved even after hundreds of million years after orogeny has ceased, with on the right-hand side of the cross section more than 40 kilometers thick crusts, and in the middle side of the section slightly more than 20 kilometers. So we do have this range of variability in this experiment that we do observe in nature. This was the first slide I've shown you with the 40 kilometers average thickness, but we can have maximum value up to 60 kilometers and minimal value down to 30 kilometers. So this was the end of the detour we took to guide you through this series of experiments that I am exploring in order to understand the formation and preservation of high temperature, ultra-high temperature terrain. What we've shown in this first series of experiments is that the interplay between the weakening associated to partial melting of the crust and the strengthening associated to the formation of granulite or strong garnet parks in rocks, and how their strain-dependent retrogression interacts, are three components that are essential in order to form and preserve crystal thickness heterogeneities, crystal roots, in the absence of magmatic heating or magmatic underplating. So this is a possible explanation for this. Of course, these are really first order model. As a hard rock geologist, I've always struggled with the simplicity of the models, but important is to get the first order idea and how these experiments can make us think about what we can observe in nature. Is everything okay? Do you bear with me? So let's now go to the second part of the presentation and build on the first series of experiments in order to understand, towards understanding and finding some possible explanation for the formation and preservation of granulatic magmatic terranes. And in this series of experiments, I will use the same principles of for the modeling I've presented before, with the same phase change and metamorphic phase changes implemented to build on a slightly more complex series of experiments. But before going into these experiments, let's step back and think a little bit about what are the orogenic styles associated to supercontinent formation. On one hand, we can have a granulite-dominated belt, really long-lived, ultra-high temperature terrain associated to supercontinent amalgamation. For example, Gondwanas, this is the supercontinents I'm more acquainted with. For example, in this map, which is taken from a compilation from Alan Collins and co-authors a few years ago, this is a map of Gondwana with down here we can see the southern granulite terrain, Sri Lanka, Madagascar, Antarctica is over here, and all of Africa. And all these terrains have recorded long-lived metamorphism associated, ultra-high temperature metamorphism associated to Gondwana amalgamation. If we look very briefly into the geochronological record, for example, in the southern granulite terrains, in the different blocks or sub-blocks of the southern granulite terrains, it is not of importance from now. The crust was hot during at least 125 million years, from 625 million years up to 500 million years. So the crust was hot for a long period of time. The witness of this ultra-high temperature metamorphism, it has been shown that it is recorded at regional scale. But I can't resist showing you one of these beautiful, iconic metamorphic assemblages that has been only recorded or found a dozen of times in the world, which is this beautiful symptoctite. Please look at the scale. This is only 200 micrometer scale. This is a sapphirine quartz integrose included in garnet, and sapphirine quartz is really records ultra-high temperature condition above 1000 degrees. This is one of the localities we've discovered in southern India. So the rocks record this ultra-high temperature condition as at regional scale, but when we have the right composition, it does record really exceptional assemblages as well. On the other hand, looking at different kind of ancient origins, I'm talking with Patrice, who knows the Variscan belt in Europe as well. We notice that maybe there is as well a different kind of orogenic style. If we look in the Variscan belt in Europe, in this tiny inset over here, this is the contour of France, of Spain, and all these dark blue domains are the places where the Variscan orogen has has been archived and is recorded and perhaps out. The left-hand map here is a zoom on the French Massif Central. I will not detail this geological map, this simplified geological map. The only thing I would like to notice is that all the colors, which are purplish, reddish, pinkish, orange, are granites or migmatites. So as a result of partial melting. And only having a quick look, you can notice that at least 70% of the rocks that crop out are migmatites or granites. Like this is a beautiful cordierite-bearing leucosome in the Velay granite. This pinkish granite over here with this centimeter-sized cordierite. So on one hand, we have this ancient Proterozoic orogeny dominated by granulite. On the other hand, we have more orogeny dominated by migmatite and granite. And we'll try to explore that through our numerical models. For this series of models, I've performed quite a lot in the past months. I will show you 3 different models. I've chosen 3 different models. We'll build on the conditions I've worked with and described in the first part of the talk. But now, in that case, we will mimic orogenic cycle with 3 steps. First, we start with the initial conditions. This yellow domains is the crust. We start with a 40-kilometer thick crust. And we choose the climatic conditions so that it shortens and that the crust thickens up to 60 kilometers. In the second step, we will mimic a delamination phase and increase the heat, the basal heat flow given at the bottom or entering our model box from the bottom, mimicking a delamination phase. And then when we have this 60-kilometer thick crust, again, we let it collapse, gently stretching on the boundaries of the box, gently stretching. What we found is that we keep the mechanical parameters constant, so the viscosity, the density of the different rocks that are taken into account, and we will only play with the thermal parameters and only explore the thermal parameters, which is basically the Moho temperature, which depends on the radiogenic heat production of the upper crust on one hand, and on the basal heat flow, so the heat flow which is coming from the bottom of the box. So playing only with these 2 parameters, I would like to show you that we can find or yield 3 kind of quite different models. So this slide is a little bit boring, but these three models, the 3 columns over here, what's important to note is our reference models will have a Moho temperature about 500 degrees, which can be close to a Phanerozoic orogeny. For granulite forming models, we'll have a really hot Moho temperature at the beginning, 750 degrees. For the migmatite model, around 650 degrees. The basal heat flow is quite similar and quite classic as well, around 0.020 watt per square meter. What is interesting and what I will develop as well as a discussion is that we've played quite a lot with the radiogenic heat production from the crust, and this does play a key role to unravel between models. In the reference model, we'll have an uniform radiogenic heat production in the crust, so 0.75 microwatt per cubic meter, and 10 times more for the migmatite and granulite models that I will present. What is interesting is the cross-section on the left-hand side, is that we've chosen to have quite high radiogenic heat production for the rocks at the surface, which is 5 microwatt per cubic meter, and gently decreasing at the bottom of the crust, reaching 1 microwatt per cubic meter. Please remember this value, 5 microwatt per cubic meter for the rocks at the surface. This is something I will discuss at the end of this presentation. But first, let's have a look at the models. First, have a look at the reference models. It could be a phanerozoic orogeny. We start with the initial condition, our 40 kilometer thick crust. We shorten the box. We thicken the crust up to 60 kilometers. We let it, increase the basal heat flow, mimicking a delamination phase, and we thin the crust again, like stretching on the bottom right side. If you would have a partially molten rocks, it would appear in purple. If you would have granulite, it would be brown. If you would have retrogress crust, it would be pale blue. So the conclusion is with these reference models, they could mimic a phanerozoic orogeny with an overall cycle duration of 30 to 50 million years, with quite fast shortening rates in the first phase. Initial Moe temperature at 525 degrees C, a uniform continental orogenic heat production at 0.75 microwatt per cubic meter, and quite a classical basal heat flow. The conclusion is we do not form large amount of granulite or migmatite using these thermal parameters. So how can we form granulite and migmatite? Let's first have a look of one of the movies. So we start shortening the crust. We create this partially molten layer at the bottom of the crust. The Moho temperature is quite hot, 750 degrees, so it allows the rock to melt. I just wanted to speed up a little bit the movie. Oh yes, I can access the scale bar to speed up the movie because it is quite long. So we have, for this model, quite slow shortening rates, which means that the entire shortening period will last around 70 million years. Already at 13 million years, you notice this brownish layer at the bottom of the crust, which is a thick granulated crust being formed. In the middle, a thick, partially molten crust layer, and in orange still the pristine continental crust. I speed up a little bit the movie now. With time, we can form a really thick granulatic crust at the bottom of the crust. And now it is in the third period, we are stretching gently this thick crust. And during this stretching, it's like 92 million years, when we return close to normal thickness, we are now at 50 kilometers of the reach back 50 kilometers for the entire crust. We still preserve like 30 kilometers of the thick granulatic crust with 10 kilometers of this purplish layer of partially molten rocks and only 10 kilometers of upper crust still over here. I have to confess that we've tried quite hard to exhume this entire granulite to the surface, but in one single orogenic phase, we haven't really managed to get everything, all these terranes to the surface, but actually reading into the literature, it's well possible that there are some subsequent orogenies that help make the last denudation and of these terranes. But this is now beyond the scope of this presentation. Just wanted to point out this fact. So if we look at the screenshots of these models, on the top left side is the initial condition. The Moe is hot, so it's partially molten, it's quite thick here in purple. After 70 million years, the end of the shortening phase, we have a thick granulatic crust. After delamination, it's even a little bit thicker. And after collapse, at the end of the collapse phase, 125 million years, we still preserve a thick granulatic and to some extent migmatic crust. So the third model I would like to show is what I call migmatic one, in which we start with an initial MOHO temperature of 650 degrees. In that case, I'll speed up a little bit the movie, 11 million years. So the shortening is also quite slow. The end of the shortening phase is like 70 million years. The crust starts to melt, and this is dominated by melting. At the end of the shortening phase, which is this screenshot over here, we have 40 kilometers of partially molten crust here in purple, a tiny pot of granulite here in brown. After the delamination, even more of this granulitic lower crust. And after the collapse phase at 125 million years, we still have a fair amount of granulite and migmatite. So this series of numerical experiments, we highlight the importance of an elevated radiogenic heat production of the upper crust. We do not attain this result if we only increase the basal heat flow that coming from the bottom of the box. So the radiogenic heat production of the upper crust is essential. And the long-lived orogenic cycle associated to slow shortening rates, which is usually associated to supercontinent assembly during the Proterozoic. And these two parameters the interplay between these two parameters seem to be a key ingredients for a possible explanation for the formation and preservation of high temperature, ultra high temperature terranes. So in the last 5 minutes, I would like to show you that using these elevated upper crust radiogenic heat productions does make sense, and it is recorded in rocks as well. For example, these are some radiogenic heat production measured on rocks which are exposed here in Central Australia. This is some work that has been done by Martin's and group from Adelaide, a recent paper published by Alessio et al. Basically, the background values for the radiogenic heat production of these rocks that are exposed in Central Australia in these bluish, pinkish colors, around 2 to 3 microwatt per cubic meter, but we can have spikes here, these reddish dots, up to 20 microwatt per cubic meter. But this is not only an Australian story. Looking at the literature, in this compilation on the left-hand side from Senthil Kumar et al. And showing some measurements from the Eastern Ghats in India, they showed that whether it is in Archean chinokite, pellitic granulite, Proterozoic pellitic granulite, or chinokite, if you look at the scale at the bottom, the x-axis values can be up to 4 to 5 microwatt per cubic meter, which are the same range of value we've used in our models. And just to for the stories, the highest value, to my knowledge, that has been recorded are in Namaqualand in South Africa, which is a recent paper from Andreoli et al. These are gamma exposure map, which can be converted in terms of radiogenic heat production. For example, in the Valputs area in Namaqualand, these red dots can be converted into values of 46 microwatt per cubic meter and be quite high. In a way, it does make sense that the Proterozoic sediments or metamorphosed sediments can be quite highly radiogenic because these are the product of the erosion of Archean terranes. So it may be concentrated in uranium and thorium. Finally, this idea of putting forward long period of time, long-lived ultra-high temperature terrain and heat production of the rocks has been already around for 10 years ago in this paper from Chris Clark in Elements. I think the title was something like, why does the crust get so hot for so long period of times? And I just took one screenshot of his paper, which I think is quite nice, because we've shown that these two parameters are quite important with a slightly different and complementary approach. It confirms same results. So let's have a look at this as this slide. Over time in x-axis, we can look at the temperature in y-axis of rocks located at 40 kilometers in depth. And this temperature of these rocks located at 40 kilometers in depth depends on the radiogenic heat production of the rocks from the upper crust. And these are these different curves. If the upper crust radiogenic, the rocks of the upper crust, the radiogenic heat production is 1 microwatt per cubic meter. This is this curve down here. The rocks would not reach more than 400 degrees at the bottom of the crust. But if we look at this gray curve up there, this is a model for an upper crust radiogenic heat production of 4 microwatt per cubic meter, and we have all these different values in between. It means that the more radiogenic the upper crust is, the more likely the rocks in the lower crust will be hot, like can reach even 1000 degrees, with a peak which is 60 or 80 million years after orogeny has started. So the same key ingredients have been put forward by Chris Clark and collaborators 10 years ago, and we've kind of confirming that these parameters are possible explanation for the formation and preservation of ultra-high temperature terranes associated mostly to supercontinent assembly in the Proterozoic. Finally, and this is my last slide, as a conclusion, the bottom screenshot of a model is a screenshot of a model I've run a couple of months ago. It's not quite actual in the parameters, but I really like it. It's the first time I saw that at the bottom of the crust here, we have some migmatitic layer here in yellow, some granulitic pods here in red, and continental crust. These are bimodal terrains. When I remember going to the field in India 20 years ago, it was quite heterogeneous with like granite, charnokites, migmatite, granulites, partially molten rocks. And if we exhume this part, to me, it looks quite similar at the first order. Of course, we are not at the same scale. This is 400 kilometers box, and we all know from the field, our field geologists, that these heterogeneities can be at much different scale. But I get the principle is the same, the first order principle is the same. Finally, now I'm working towards extracting pressure, temperature, time pass of different particles from these models, or depending on strain rates and phase change and all that, in order to compare the predicted particle trajectories from the models to natural data that we can get through petrochronology of these rocks from this terrain. And because I believe that rocks can archive geodynamic processes, and they must be strong anchor point to see whether our models, our experiments are realistic and how they can record geodynamic processes. So to me, with this very different background I could gather, is what is important is the conversation. The conversation between the natural data we can observe and we can quantify, like petrochronological data or field data, structural data, geometry, and the ideas we can get when running some experiments. And important is this bridging the gap between discipline and talking between disciplines that will help us understand these first order genomic processes. Thank you for your attention.